The derivative of ln of x is equal to 1 over x, and this is one of the most well-known derivatives. And this result may seem kind of random, but it's actually not that hard to prove. What I'm going to be doing in this video is proving this common result. The proof relies on knowing that the derivative of e to the x is e to the x. So I'm going to assume we already know this is the case, but I already made a video on the derivative of e to the x, which I'll link in the description. So the first thing we should do is let y equal ln of x. The goal here would be to find an expression for dy dx, which would be the derivative of ln of x. If we apply the exponential function to both sides, we get the relation e to the y equals x, since on the right-hand side, the exponential function cancels out with the natural logarithm function, because of course, by the exponential function, I am referring to the exponential function of base e. If we take the derivative in respect to x on both sides, the left-hand side becomes e to the y dy dx, since when we apply the chain rule, the derivative of e to the y in respect to y is still e to the y, and we also have to multiply this by the derivative of y in respect to x, according to the chain rule. This is of course the part where we have to assume we already know the derivative of e to the x. The right-hand side becomes 1, since the derivative of x in respect to x is just 1. To isolate the dy dx expression, we need to divide both sides by e to the y. If we do that, we get dy dx equals 1 over e to the y. We established earlier that e to the y equals x, so 1 over e to the y is equivalent to 1 over x. So dy dx equals 1 over x. We started with y equals ln of x, and we ended up with the result dy by dx equals 1 over x. So the derivative of ln of x is 1 over x, which was what we were trying to prove. This was kind of a short one. Once we know that the derivative of e to the x equals e to the x, it's not that hard to apply the implicit differentiation to find the derivative of ln of x.